So thanks for giving me this challenge. So yeah, so I really enjoyed building. So let me through walk you through the architecture. Yeah. So basically, we have two main data sources from the kernel. We have a process execution, we have Tetragon, which is a eBPF monitoring and observability tool. And then we have the packet inspection via custom eBPF, which hooks itself to TCP send message. So Tetragon is great for process level visibility and basic network metadata, but if I found that it doesn't expose an actual payload bytes in the events, right? So for through DPI, especially like detecting secrets like GitHub tokens being exfiltrated. So for that, I wrote a custom eBPF program that reads up to around 502 bytes of TCP payload from the kernel, and then stores it via ring buffer and then sends it to Go agent. Go agent is basically an orchestration layer of our project. It converts all of these events into a structured data, in our case JSON format. It then sends it to open policy engine. Open policy engine basically takes two arguments: structured JSON events and the policies that we have predefined, and based on the policies and the events, it compares it and it comes to the conclusion whether the particular event matches with the policies or if it's going against the policies, and then a alert is being fired, and this everything happens at the lifetime. I would love to show you. So we have this project going on. So I've named my project Kratos. So Kratos is basically a eBPF. We loaded up policies. All those policies are loaded. Policy agent has been loaded. We have connected to Tetragon, and DPI has been attached, which means all of our components have been attached, and it is like watching every single syscall and network that metadata that is happening. So right now, as you can see, everything is clean, which means it is not violating any of our policies. But now you see a process. Why? Because what I did is I executed a curl command, which basically tries to exfiltrate a secret. So now let's try it once again. And yeah, this is a curl command which has a secret GHP, which is a GitHub PAT token format. And now I'll do this. Now let's see the output. This is all live data that is happening. Let's wait for a while. Yeah. So as you can see, critical vulnerability has been spawned. So we ran this. We executed a shell in a production environment, and it shelled us an alert because it's a critical severity, because it is a namespace, right? Let's try something. Uh, yeah, we'll do a curl. This is a fake token. We'll try exfiltrating. Now let's try if it monitors. It takes time because there are a lot of things that are going on inside the system. Let's try a better version attack instead of this. Let's try this. Yeah. So here we are in Ngix production. We are running this command. Uh, Now let's see if it catches it. Yes. Yeah. So we could say it's a GitHub PAT exfiltration attempt. So now you may ask that why are there so many events about GitHub exfiltration? Why is there one? Because what happens is that everything, the reason you say for critical alerts for one command, because the same sensitive data flows from multiple kernel context, right? It first from curl processes and container, then kubelet. A custom eBPF hook captures the payload at each of this point, and this gives very high visibility into exfiltration attempts since we can detect AWS keys, bearer tokens, and etc. Uh, so yeah, so like for I will have to show you the code. So these are our policies, process policies and network policies. So now in process policies, we could say shell in production. We got a critical severity because we spawned the shell in a production namespace. If we had spawned the shell in other namespace, it would be a high vulnerability. We saw a network. So we saw the example of GitHub. We saw this example of GitHub. We saw that we have AWS key similar. We have similar. We can do it with bearer tokens. So there are a lot of options that we could use. So yeah, that was our project. I've learned a